Good evening, everyone. So this is Eschan Rakesh Roshan. So the title of my talk would be Design Principles for Materials with Extreme Lattice Thermal Conductivity. So the outline of the talk is as follows. So basically, I'll just talk about what is lattice thermal conductivity, concepts related to that, and why do we need to calculate that, and how do we calculate it, the methodology and the computational tools that we have used. And I'll also talk about the strategies, that we have come up with, for the design of low KL materials, that is low materials with low lattice thermal conductivity. So yeah, for any material, as you all know, the maximum efficiency of thermoelectric material is given by its basically figure of merit. I mean, we want it to be as high as possible. So that ZT, the figure of merit, is given by S square sigma T divided by Ke plus KL. So here S is in the numerator first, S is the Seebeck coefficient, sigma is the electrical conductivity, T is the temperature, absolute temperature. And in the denominator, we have Ke, which is the electron thermal conductivity, and KL, which is the lattice thermal conductivity. So basically here the idea is to optimize ZT or to maximize ZT. So in order to do that, we can lower KL. So you can see that that is in the denominator. So if you lower KL, indirectly you are like increasing the ZT value. So here there are two things. I mean, you can see KE and KL. I mean, we can work with either of them. KE basically deals with the electronic transport, and KL deals with the phonon transport, or that's what we are calling it as lattice thermal conductivity, which is basically caused by the heat transport, which is basically caused by the phonon movement. So I worked to lower KL in the current work that I'm presenting. So electronic transport, you can generally optimize it by using the band tuning and by doping also. Whereas the thermal conductivity, you can do structural engineering, and then you can basically limit the phonon transport. You can slow down these phonons. Why are we studying this? I mean, what is the necessity of having low KL materials? I've just shown you the applications here. We can use these materials as thermal barrier coatings in in heavy machinery which are working at high temperatures. Excuse. You can also use them in solid state energy conversion devices. And basically, you can use them as thermal insulation like in colder countries, like you want the room to remain heated. Once the sun is on, the room gets heated, and in the evenings or night you want it to be the heat to be retained. So basically you can use these as building envelopes, like outer shells of thermal storage tanks. And you can also use them as thermal barriers between the individual cells in a battery pack. By any chance, if one cell goes off, catches fire, you don't want it to carry forward into the next set, so you can use these as barriers. Okay, so these are the applications of having materials with low lattice thermal conductivity. So the methodology that we have used is the density functional theory, and this is one of the most successful approaches for computing the electronic structure of matter. And the applicability of this ranges from almost like atoms to molecules and solids. And basically, we get the information about the ground state properties of the system. As the name suggests, it's called as density functional theory. I mean, here it is a function of a function. So electron density is taken as the function here. That's a prime thing with which we work on. And using this, we calculate the ground state properties. And with that, we obtain the other properties that we are looking at. So next question is, how do I apply DFT for material science? I mean, so what are the steps that are involved? So first most thing that we need to do is we need to translate our problem to a computable atomic streak model. That's very important. And once we have the model in place, then we need to compute the required properties that we are targeting. In our case, it is having or getting low KL, and these results that we get, that we get by using DFT can need to be validated by confrontation with experiments. So basically, it's like theory and experiment should have a good synergy. They should go hand in hand. So we'll be able to predict good properties, and we can obtain advanced functional materials using this methodology. So what all properties could be studied in general? I mean, we can study the band structure of a material. Like band structure is nothing but a plot between the energy and the wave vector. We can also obtain the density of states. We can also talk about the stability of a system, the dynamical stability at a given temperature or pressure. I mean, whether the given system is stable or not by calculating the lattice dynamical properties. And we can also calculate the mechanical properties and look for the mechanical stability using the elastic constants, bulk modulus, rigidity modulus, and all of that. And we can also talk about the nature of the substance depending on the values that we get. Is it ductile? Is it brittle? All of that could be studied. And in the current work, I mean, I am focusing on transport properties, where we look at the phonon transport, and I basically calculate the lattice thermal conductivity based on this. So the computational tools that I have used for this work are Quantum Espresso. This is open sourceware. I mean, so and WASP. WASP stands for Vienna Ab Initio Simulation Package. This is a licensed package. We have a license for that. And TDEP, temperature dependent effective potential. So this we have used to calculate the lattice thermal conductivity. And Vesta is a visualization for electronic and structural analysis. Basically, this is a software to visualize the atomistic models. So Quantum Espresso generally people use for band structures and ground state calculations. WASP also we can do the same. So we have used WASP in the current work, and combined with TDEP. Yeah. So the workflow is as follows. Basically, we collect the structural information from open source databases like Materials Project and other websites where the structural information, CIF files about the materials is available. And then you make a primitive cell. So this is generalized one, okay? So make a primitive cell, and then you optimize it at 0 Kelvin. And using a primitive cell, you create a supercell, because a supercell is one which resembles much closer to the realistic system. And then you perform the MD simulation, molecular dynamic simulation on that for 2 to 3 picoseconds. And from that, basically, we extract the second, third, and fourth order IFCs, interatomic force constants, by fitting the forces to the model Hamiltonian. So here you can see you can have higher order terms. We have restricted ourselves to third order, because the more orders that you include, computationally much more demanding it becomes. So we have stopped at third order, and that gives pretty decent results. And from this, we compute the phonon dispersion curves, or the density of states, granulation parameters, lifetimes, group velocities, and using those, we can obtain the lattice thermal conductivity. The formula is given here. So it is 1/3 of CV square tau. C is the specific heat, V is the group velocity, excuse, tau is the phonon lifetime. And ultimately, once we get the values, we can screen out the materials which have low thermal conductivity or ultra low thermal conductivity based on the application that we are looking at. So these are the results. So basically, the compounds that we have studied are alkali halides. So as you can see, My compounds. M stands for lithium, sodium, K, Rb, and cesium, and Y stands for F, Cl, Bri. These basically in the ground state. I mean, at ambient conditions, basically they crystallize in the NaCl structure, except for CSX compounds, cesium chloride structure. Rest all are like they crystallize in the NaCl type structure or B1 type structure. So I'm showing the results for the obtained KL values at different temperatures. Starting from 0 Kelvin, we have gone up to 800 Kelvin. So the first observation that we need to make here is, as the temperature increases, the lattice thermal conductivity decreases. So the same thing is observed in all the studied compounds. And you can see at higher, as the temperature increases, the KL value decreases. And for some compounds, you can see that KL is almost less than 2. For example, in this case, if you look at KF, KCl, KBr, KI, so for these you can see it's almost 2.5 or something like that. Okay, I'll show you clearer values once we go forward. And the next thing that we did is we have obtained the phonon dispersion curves. As I was just mentioning, phonon dispersion curves basically tells us about the dynamical stability of these systems. So what we have done, we have obtained the phonon dispersion curves at room temperature. And as you can see, so here, basically a phonon dispersion curve is a plot of the frequencies along the high symmetrical directions. As you can see, along the x-axis, you have gamma x, omega k, gamma l. These are the high symmetry directions that we have taken. And you can observe that in all the studied compounds, the frequencies are positive. So you do not have any negative frequencies. That indicates that all the studied compounds at room temperature are stable. So this is most important thing. If it is not stable, there's no point in studying about it. I mean, there's no point, because you cannot, if you make it also, it's of no use, because the system will not be stable. The compound will not be stable at that, under those conditions. Here the condition is at room temperatures. So the confirmation is the systems, all the systems which have been studied are stable, dynamically stable at room temperatures. So once we are convinced with that, then we have calculated the phonon lifetimes. So I have shown you for 12 compounds over here, Na series, Li series, and Kf series. So one thing that you can observe is, as the size of the anion increases, that is, as you go from F to Cl to Br to I, you can look at any of the figures. Let's say you look at this figure, you can see that as the size of the anion, that is F to Cl to Br to I, as you move, as the size of it increases, you can see that the phonon lifetimes come down. So if phonon lifetimes decrease, basically, as I've shown you some time back, KL is proportional to tau. So lower the phonon lifetimes, lower is your lattice thermal conductivity. And we also calculated the group velocities. The relation between KL and group velocities is also directly proportional. So you can also see, once again here, for example, once again, let me just show you NaX series. You can see the black one is NaF, followed by the blue one, which is NaCl, the red one, which is NaBr, and the green one, which is NaI. And as you can observe, that the group velocities are also decreasing as I move from F to I. So basically, you can see a proper pattern that's being observed in all the studied compounds. And we have plotted the spectral and the cumulative lattice thermal conductivities at different frequencies for all the studied compounds. Here, these lines on the solid lines, basically they represent the cumulative lattice thermal conductivity, and the shaded regions on the left side, they basically represent the spectral thermal conductivity that we have obtained. And we have also looked at the mass ratio plots, and we have plotted them. So basically, mass ratio is the ratio of the bigger size to the smaller size. For example, if you're talking about NaF or any other compound, so either ratio of cation to anion, whichever is bigger in size to the smaller in size. And you can see that we have highlighted one particular region where the mass ratio is closer to unity, and we looked at it and we came up with some design strategies. You can see that KCl, for example, RBBr and CSA and NAF, I mean, they're all lying closer to the mass ratio being unity. So, and on the right side, I have plotted the different other parameters like specific heat, for example. So CV, this I have just blown up this region and then plotted it over here in the B from A. And then I have plotted the debye temperature, and this gamma V stands for the Grunewald parameter. So larger is the Grunewald parameter, greater is the larger thermal conductivity. So same is the case with debye temperature. Lower is the debye temperature, lower would be the lattice thermal conductivity. So basically, we have obtained all these parameters, and we have plotted to see if there is any correlation that exists between these. What we could see is we could see a correlation that is observed between the mass ratios, and rest all is okay. I mean, so the key findings that that are there from our work, the critical insights are as follows. Whenever the difference between the atomic masses is minimal, which means the mass ratio is closer to 1, it significantly boosts the contribution of optical phonons to the KL, and this results in an increase in the KL. So as I've shown you that line where the this region, this line where the mass ratio is 1, so all those which are closer to 1, these materials had a greater KL value. So among materials with a mass ratio close to unity and low atomic masses within a binary system, they exhibited more dispersive optical phonons, and these phonons made a substantial contribution to KL. So here in the phonon curves, the lower frequency ones, let me just go back quickly. So here you can see, you take any of them, you can see, for example, here there are 6 branches, take any of them. Lower ones are the acoustic phonons, and the upper ones are the optical phonons. You can see in some cases that there's an overlap. For example, H, let me come to H and CSI, that's CSI. You can see that there's an overlap between the optical phonons and the acoustic phonons. And in other case, let us talk about C, you can see that there's a phonon gap over here. So there is a difference between the top ones and the bottom ones, that is between the optical phonons and acoustic phonons, there's a phonon gap that exists. So in the case of H, there's an overlap that is happening. So optical phonons are falling into the acoustic region, and they are contributing to the thermal conductivity also. That is how you are getting a higher thermal conductivity. So let me just go back to the findings. Yeah, conversely, materials with a mass ratio close to unity but heavier atomic masses, they display less dispersion among the optical phonons and relatively smaller contribution. So in general, looking at all of these results, so we came up with a conclusion that whenever you have materials with a mass ratio approaching unity, so they tend to have longer phonon lifetimes, which means you will get a high KL value. So this remains a dominating factor in achieving high K values. So the conclusion is materials composed of elements with similar atomic masses will exhibit higher values of KL. And these are all the data that we have got from the work. So lattice constant, average mass, velocities, debye temperature, gradation parameter, specific heat, mass ratio, and lattice. So in the last column, you can see all the KL values that you have got, and you can see, for example, for CSBR and CSCL, you can see that we have almost like 1.5 and 1.46. These are very small. The lattice, it's almost like a very low lattice thermal conductivity values that we have got. So all the overall summary and the conclusions from the current work are that the low-lying phonons, they are contributing significantly to the phonon transport to enhance the KL in the materials like NAF, NaCl with a mass ratio close to unity along with their average atomic mass, and the relatively low scattering rates. So basically lower lifetimes indicate the scattering rates are exactly inversely proportional to the lifetimes. So relatively lower scattering rates for materials with a mass ratio close to unity result in high phonon lifetimes, and thereby that results in an enormously high KL in any given series. So overall, the phonon scattering rates, which is nothing but inverse of phonon lifetime, they play a predominant role over the phonon group velocities in determining the trends in KL for alkali halides with mass ratio close to 1. And the present study provides an in-depth understanding of the atomic mass and its effect on phonon transport properties on the alkali halides. So furthermore, by using this, since we have looked at a series of compounds, we can see that by manipulating the atomic masses, we can engineer materials with both high and low KL values. This provides very good possibilities for tailoring the lattice thermal conductivity for various applications. And the work that I have shown is from the top one. So these are the publications that we have published this year. The top one is the work that I have shown you, effect of atomic mass contrast on lattice thermal conductivity, case study for alkali halides and alkali chalcogenides, which is published in ACS Applied Electronic Materials. And we also did a similar work for alkali chalcogenides in 2022 last year, and that was also published in ACS Applied Energy Materials. So so thank you for your patient listening.
The title of my presentation is Bandgap Engineering of Nanostructures UDC Thin Film. Cadmium selenide. Cadmium selenide is a 26 N-type semiconductor, and the bandgap of CDC is 1.7 electron volt, which is in the visible region, and its bond acceptance diameter is 12 nanometer. CDC has three crystalline forms, existing three crystalline forms in woodsite, extrarite, and rock salt, and copper selenide, which is the 216 and T-type semiconductor, which can exist in four phases. One is in cubic, monoclinic, orthorhombic, and tetrahedral phases. The material.
Dr. Sajid?
Yeah.
Sir, please switch on your camera.
Okay. Please.
Are you sharing this from mobile?
Yeah. Okay.
Okay. But your slides are not visible. Yeah. Yeah, that's good.
Okay.
Carry on, sir.
Yeah. So copper selenide is a 1,6 and P-type semiconductor, which is existing cubic, monoclinic, orthorhombic, and tetrahedral phases. The material has an indirect band gap of 1 to 1.27 electron volt, which makes it an absorber material. And the direct band gap is in between 2 and 2.3 electron volt, which makes it an window material for. And actually, my topic is in nanocomposite material. A nanocomposite material is a composite of two or more phases with at least one among these phases having nanoscale structure. The nanocomposite of N-type CDC and P-type CDC semiconductor are important in applications for optoelectronic and including photovoltaics. Actually, I am going to present my topic in this composite of CDC and CDC. The applications of CDSC is in thin-film transistor, solar cells, light-emitting diodes, photoconductors, photovoltaics, and in nanosensors. And the applications of C2C actually is in optical filters, supraionic conductors, power control coatings, photovoltaic electric devices, thermoelectric conductors, and in window materials for solar cells. So for the preparation of synthesis of CDSC, C2C thin film, we are deposits on glass substrate by co-evaporation of CDSC and C2C powder for different weight percentage of C2C conversion. Actually, we have taken the weight percentage of C2C is 5%, 10%, 20%, and 30%. And we have used the deposition pressure for this composite is 1 × 10⁻⁴ millipar. And the characterization of samples and studies we have done is PDX, XRD, AFM, XPS, micrometer spectroscopy, UV visible spectroscopy, and the studies in DC electric conductivity. And the energy dispersive X-ray spectroscopy, we have got, actually we have recorded 4 spectra for CDSC C2C thin films for 5%, 10%, and 28% and 38% for radial spectra. The atomic composition we have obtained is incorporated the samples in CS5, CS10, CS20, and CS30 were 3.87, 9.24, 17.72, and 29.86 respectively. The third spectra of these 4 samples, actually we have gotten index peak at 25.4 degree for the reflection. So index peak at 002 reflection, and we have also got weak peaks at 24 degree and 42 degree, which corresponds to 100 reflections and 110 reflection points of CDSC. Whenever the concentration increases, we have got at 20% and additional peaks at 26.8 degree, which is 111 reflections of corresponding to C2C phase, which means that C2C exists as a nanocomposite in the 20% weight percentage of C2C, and whenever the C2C composition increases, its intensity of the C2C peak increases. This is actually an enlarged images of 111 reflections, which exactly sees that the intensity in 111 reflections of the C2C peaks increases with the weight percentage. These are the sample composition details. Sample codes were used CS5, CS10, CS10, and CS20 and CS30. The thickness we have got is 104, 1 ton, 161, which means that the thickness increases. And the grain size calculated from Sharrow formula, using our Sharrow formula, we have got 33.05 for CS5, 31.1 for CS10, 29 for CS20, and 26.8 nanometer for CS30 sample. And the XPS spectra, we have recorded XPS spectra for CS5 and CS20, semi low percentage and the 20% C2C weight sample. We got the peaks, elemental peaks at the CD, cadmium 5/2, cadmium 3/2, and the copper peaks and selenium peaks also we have observed with surface scan. The in-depth scan of copper peaks, we have got CO2 2P 3/2 at 932.3 electron volt and 2P half peak at 952.1 electron volt, which means that Cu is exists at +1 oxidation state, and the intensity of this peak increases as the percentage of C2C peak increases. Actually, we have not obtained the satellite peak, which means there is presence of Cu2 plus actually is not observed in the XPS spectra, which means the Cu exists and 1 + 1 oxidation. These are the core level peaks for CD3D and CD3 peak and selenium 3D peak. For CD3D, we have got CD3D 5/2 and CD3D 3/2 peaks at 405.1, 411.9 electron volts. And for CD3D peak, 3P peak, we have got CD3P 3/2 and CD3P half peaks at 18.6 and 59 electron volt. And for selenium 3D peak, we have obtained at 53.8 electron volt. These are the AFM images. AFM images actually, from AFM image, the samples actually in the spherical shape, and its size decrease with the increase in the size C2C weight. The micrometer spectra of films we have obtained also recorded. We have got one L of peak set 207 to 207 centimeter inverse, and the overtones for 11 centimeter inverse, and also 619 centimeter inverse. And an additional peak was observed at 258 centimeter inverse, which shows the CU2SC presence of CU2SC. And the intensity ratio for 2LO to 1LO for the filling percentage, 5%, 10%, 20 and 30% was obtained, 0.32, 0.31, and 0.3 and 0.29 respectively. That means the intensity ratio decreases as the C2C weight percentage increases. So optical transmission spectra of the samples also recorded for the 4 samples, and as the C2C weight percentage increases, we can observe the blue shift of the respective samples or increasing the weight percentage. And also we have plotted the band gap values for top rods, and for first CS5 for 5% we got only one band gap values, and as the percentage increases, we have obtained 2 band gap peaks corresponding for CDSC and C2SC. This band gap value increases with the increase in the weight percentage. And DC electrical conductivity. DC electrical conductivity also record for films. In conductivity increases with the increase in the temperature, which confers that semiconducting nature of the present films. At room temperature, the conductivity of the values approximately at 2.6 into 10 raised to minus 3 for CS5, and 1.2 10 raised to minus 2 for CS10, and for CS20 film, we have got around 1.94, and for CS30%, we got around 2.72 into 10 raised to minus 2 form inverse centimeter inverse. The conductivity increases with increase in the temperature, and also conductivity increases with increase in the C2C weight percentage. And we have also determined the band, also determined the activation energy using the RLS plot, and the activation energy decreases with increase in the weight percentage of the C2C, which means that the conductivity increases with the increase in the C2C weight percentage. This is the Hall measurement we have got for 2. We have recorded for 2 films, CS20 and CS30 weight percentage. The mobility of the film decreases as the temperature increases. These are the energy level of the CDSC and C2C, which we have determined using Anderson model energy band diagram. The conduction band values. The conduction band of delta EC for electrons we have determined using the equation chi CDSC minus chi C2SC, and the valence band of we are recorded using for hole for equation 2. And for the 2 films CS20 and CS30, we have got delta EC values for 0.46 electron volt and delta EV values for 0.19 electron volt CS20. And for CS30, delta EC values for 0.44 electron volt and delta UV values 0.26 electron volt for CS30 films, which means that the delta UV values decrease, which means that the EC conduction path for all from CU2C to CDSC. Sorry. Clock. And for conclusion is nanostructure CDC, CTC contain different weight percent of CTC were prepared by cold evaporation method. The sample were characterized using different experiment technique like energy displacement spectroscopy, XRD, AFM, XPS, microraman, and UV spectroscopy. The activation energy for conduction decreases with the increase in the weight percent of C2C for sample, and the energy band diagram level determined using Anderson model. Okay, thank you.
Myself, Dr. Samit Kumar, Associate Professor in the Department of Chemistry, Faculty of Basic Science, going to present a study on preparation and physicochemical properties of green hydrogels.
Dr. Samit Kumar, please adjust your camera.
One minute. Is it okay, ma'am?
Yes, sir.
Okay. In the second international conference on recent trends in material science and devices 2023. Thank you so much for giving this type of opportunity. And in my research, I use the waste material, actually corn cob, and corn from which Jalan or hemicellulose is extracted, and this hemicellulose is used for value-added material like hydrogel preparation and its further characterization process. This is the outline of the research, introduction, proposed methodology, derivatization of Jalan to carboxymethyl Jalan, schematic.
Sir,
your screen
Dr.
is not visible, sir.
Sir, your slides are not moving. You have to click on the slide which you want to show.
It's moving,
It
ma'am?
got stuck on the first slide.
It's moving?
Yes, sir.
It's moving right now?
Yes, sir. Now they are moving.
Okay. This is the outline of our research, in which we focus on introduction, proposed methodology, derivatization of Jalan to carboxymethyl Jalan, schematic chemical representation, hydrogel preparation, proposed applications, and references. This is the introduction part, why we are choosing the corn cob, because every 100 kilogram of corn grain, 18 kilogram of corn cob approximately produced, which are remain unused as a cellulosic waste in the field and factory, which poses serious problem not only storage but also for disposal. Additionally, corn cob is processed at very low cost for obtaining the cellulosic and non-cellulosic components with value-added product. The non-cellulosic components such as Jalan has exceptional properties that is indigestible in the upper gastrointestinal tract, but digestible in the lower gastrointestinal tract by anaerobic microflora, draw more and more attention on its development and applications. In addition to digestibility property of lower gastrointestinal tract, Jalan also have several beneficial effects, including anti-phlogistic effect, immune function, inhibitory action on the growth rate of the tuber, mutagenicity activity, non-toxicity, biocompatibility, and biodegradability that create a center of attention to scientists or researchers towards the developing of value-added products such as pH-responsive hydrogels. This is the structure of hemicellulose in which acetyl group is also present. Some other components is also attached with Jalan monomer. This is the proposed methodology. Slide is moving, ma'am, or not? Hello? It's moving?
No,
No,
sir.
it's not moving.
Okay. Now moving, it's moving.
Sir, you have to just click on the slide.
Okay.
Sometimes slideshow is not working over there.
Okay. This is the proposed methodology in which corn cob firstly chopped into small pieces, and then it is mixed.
Sir, we are
Yeah.
on the introduction continue kind of slide.
It's not moving, ma'am.
No, sir.
Can I stop my setting and again start?
Sir, as you like. If you think that will be done, it's okay.
Hello, ma'am. I'm Jaiprakash, Professor Jaiprakash.
Yes, sir. Yes,
Ma'am,
sir.
It's moving,
see,
ma'am.
I have just
Yes.
Yes, sir.
Sir.
Now we are on the fifth slide. Introduction continue.
Its proposed methodology is seen.
Yes, sir.
Okay. Can I continue?
Yes, sir. Yes, sir. Please continue.
Okay. Thank you. This is the proposed methodology in which corn cob is chopped and milled into powder, and then further it is a delignified process, delignified with the help of sodium chloride, acidified sodium chloride. The delignified holocellulose was obtained. The delignified holocellulose was treated with 4% sodium hydroxide at 60 degrees Celsius, and then the filtrate which was obtained is further precipitated with acetic acid, and it is settled down with methanol. Then Xylan-rich hemicellulose were obtained. This is the chemical equation. Xylan component of holocellulose, which is dissolved in sodium hydroxide. It is ionic product, and that is dissolved, which is obtained in filtrate, and filtrate is further acidified with sodium acetic acid and settling down with methanol. Then Xylan-rich hemicellulose were obtained. Further, here Xylan is derivatized with monochlorosodium acetate to get carboxymethylated Xylan. In this process, Xylan firstly dissolved with sodium hydroxide, and then further it is treated with sodium monochloroacetate. The acetylation takes place or not, it is further confirmed by FTIR spectroscopy, in which carboxymethylated Xylan has one extra peaks at 620 20 centimeter inverse, which represents the carboxymethyl group, as here the carbonyl group actually has 1700 centimeter inverse frequency, but there is the delocalization of electron takes place, and that's why there is some lower frequency or wave number is obtained. This confirms the acetylation of Xylan to form carboxymethyl Xylan. Now, there is the preparation of hydrogel. Hydrogel is the interpenetrating network of three-dimensional interpenetrating network of polymers which absorb a large quantity of water. That is called hydrogel. For the preparation of hydrogel, per oxidized sulfate ions generate radical anions by thermally. For the synthesis of hydrogel, firstly we choose the persulfate ion, and it is decomposed uh, uh, by heat in the radical form. This anion radical abstract the protons from Jalan to form Jalan radical. Now, the Jalan radical further reacted with acrylic acid to form here radicals, which is polymerized. Now, further it is treated with NN-methylene bis-acrylamide to form hydrogel. Because it is NN-methylene bis-acrylamide act like a cross-linkers, and there is a cross-linking agent present here. This is the photographs which I have prepared in my lab by the ratio of 2:1 to 10:1. 2 mole of acrylic acid, 1 mole of Jalan. Here 10 mole of acrylic acid, 1 mole of Jalan. It means we vary from 2 mole to 10 mole of acrylic acid for a fixed mole of Jalan, and we get this type of hydrogels. These hydrogels were further characterized by the FTIR spectroscopy. In this process, here 1710 10 wave number a peak absorption band were obtained, which indicate that there is a hydrogel preparation because there is a number of carboxyl group present here. And thus black line graph is for Jalan rich hemicellulose. After the preparation of hydrogel, we observe the swelling percentage. Swelling percentage is equal to W2 minus W1 divided by W1 into 100. W is the weight of hydrogel, and W1 is the dry weight of hydrogel. And all the experiments takes place in a triplicate, and that's we obtain the average percentage of swelling here is 6,824% with the by 2:1 ratio of acrylic acid is to Jalan. Further, this is the photographs of wet and dried hydrogels of which was preparing in the lab. Now, this is the swelling kinetics. Swelling kinetics is also observed in maximum percentage with the maximum percentage by taking the amount 2:1 ratio of acrylic acid to Jalan, and it is the swelling ratio 6,000% in the time range of 10 hours to 12 hours. Moreover, the high swelling percentage may be attributed to the high porosity of hydrogel beds. This is the swelling kinetics, and it is the application part of hydrogels. And hydrogels were used in different purposes. like drug delivery system, contact lens, hydrogel scaffold, osteoporosis, gastrointestinal problems, and this is the transdermal applications. This is the hypothetical representation of hydrogel which act as a carrier for drug. Like here drug, and this is the carrier which is incorporated of covalent linkage takes place, which ultimately drugs molecule go to the lower gastrointestinal tract because Jalan is not digested in the upper gastrointestinal tract. This is the conclusion of our research. In the present study, polyacrylic acid Jalan-based green hydrogel were synthesized successfully by cross-linking of acrylic acid monomer in Jalan suspension using N-methylene bisacrylamide as a cross-linking agent via free radical polymerization reaction. The FTIR spectroscopic data showed the successful synthesis of hydrogel using different ratios of acrylic acid to Jalan. Among the successful synthesis of hydrogels, the maximum swelling was observed with 2:1 ratio of acrylic acid to Jalan at a neutral pH. The mechanical stability of synthesized hydrogels with the ratio of 2:1 of acrylic acid to Jalan may also be higher among the other ratios of prepared hydrogels. This study leads to new insight to develop stretchable and tough Jalan-based hydrogel having potential applications in cutting-edge technology areas. And that's why it's think green, go green, and this is the references which was used in my research paper. This is my research publications, and this is our research group in the students which have been working with in our groups in PhD. This is the PhD students working under my supervision. Thank you. Thank you so much for your kind attention.
Good morning, everyone. Myself, Dr. Sandeep Patade, from Depth of Chemistry, MSG College, Malegaon, Nasik, from Maharashtra. Today, I am going to present my work entitled Synthesis, Characterization, and Computational Investigation of 4,4-bromophenyl to 4-chlorophenyl 2,3-dihydro-1H benzo B 1,4-diazepine molecule. This is the general outline of my work. That first synthesis, then characterization of synthesized molecule, computational study of synthesized molecule, which includes the DFT-based structural analysis as well as DFT-based spectral analysis, conclusion and references. This is the scheme for synthesis of our title molecule. First, we take the equimolar mixture of parabromoacetophenone and parachlorobenzaldehyde that is stirred at room temperature in ethanol as a solvent by using the 10% sodium hydroxide, which gives the formation of the intermediate, that is the chalcone. This chalcone reacted with the orthophenyl diamine in using piperidine as a base, that is reflux with ethanol for the 5 to 6 higher, that gives the formation of the benzodiazepine derivative. This benzodiazepine derivative is a light brown solid, and that having the melting point 108 to the 110 degrees Celsius. The characterization of the synthesized molecule can be carried out by using spectral methods like the FTIR, H1 NMR, and the C13 NMR spectroscopy. This is the FTIR spectrum of our synthesized compound. This peak at the 3337 centimeter inverse indicates the presence of NS staging frequency, while the peak at 2920 and 2848 centimeter inverse indicates the presence of aromatic CS staging frequency. The peak at the 1680 centimeter inverse, that is due to the presence of carbon double bond nitrogen staging frequency, while this peaks 1590 and 1528 centimeter inverse, that is due to the presence of aromatic carbon double bond staging frequency. This is the H1 NMR spectrum of synthesized compound. The H1 NMR spectrum shows that there is the peaks in the deshielded region from 6 to the 8 delta value, that is due to the presence of aromatic protons, while the peak that is present in the shielded region, that is from 3 to the 4 delta value, that is due to the presence of sp3 hybridized carbon hydrogen bond, and this peak at the 5.5 delta, that is due to the presence of NH, that is the NH bond. This is the C13 NMR spectrum of synthesized compound. This NMR spectrum also well matches with the structure of the compound, that the deshielded zone of this C13 NMR spectrum shows the values of the carbon that is between the 110 to the 170 delta value, that is due to the presence of aromatic carbons, while this peak at the 37 and 70 delta value, that is due to the presence of sp3 hybridized carbon. We also carry out the density functional study of the synthesized compound by using the Gaussian software, because this density functional theory is nowadays very crucial for the investigation of the molecular structure of the compounds. Also, that is very crucial for the determine the various electronic properties, spectroscopic properties, as well as thermodynamic properties of the synthesized compound. These are some objectives for the DFT study of the synthesized compound, that to determine the optimized geometry parameters of the synthesized molecule, also to determine the molecular atomic charges of the molecule, to analyze the thermodynamic stability of the compound, also to calculate the homo-LUMO energies with their energy gap. Also, this DFT investigation of the molecule can be used for the evaluation of the various global reactivity descriptors, that is very crucial for the determine the stability of the compounds. Also, this DFT analysis helps to analyze the stability and reactivity of the molecules by using the FMO analysis and by using the MEP analysis. Our study also focus on the effect of the different solvent on the spectroscopic properties of the synthesized compound. This is the optimized geometry of the molecule, and this geometry can be optimized by using the Gaussian software at the DFT B3LIP method with the 6311 plus GDP basis set. This is the optimized structure of the molecule, which is clearly shows that this molecule having the non-planar structure, because this benzodiazepine ring as well as 4-bromophenyl ring is present in the planar structure, but this 4-chlorophenyl ring is perpendicular to the average plane of the molecule. And from this optimized geometry of the molecule, we analyze the various geometrical parameters like the bond lengths and bond angles of the molecule, and these bond lengths and bond angles of these molecules that is calculated from the DFT analysis, that is well matches with the normal values of the bond lengths and bond angles. Now in this case, the bond between carbon and bromine having the highest bond length, that is the 1.91 angstrom unit, and that is attributed due to the highest atomic size of the bromine. These are the bond angles of the synthesized molecule, and these bond angles are also well matches with the normal values of the bond angles. When we look the bond angles of the sp3 hybridized carbon, then that is appears at the 109.5 degree, while the bond angles of the sp2 hybridized carbon, that is appears at the 120 degree. These are some molecular atomic charges of the synthesized compound that can be again computed from the that is the optimized geometry of the molecule. These molecular atomic charges is can be calculated by using the two basis set, that is the 631 GDP basis set and 6311 plus GDP basis set. Now when we compare the charges by using two basis set, then it is observed that the 6311 plus GDP basis set, that is a higher basis set, overestimate the charges, but the 631 GDP basis set that gives the reliable charges. This is the molecular charge distribution of the title molecule that can be computed at the B3LIP level with the 631 GDP basis set. And this is the atomic charge plot of the title molecule, which clearly indicate that the higher set of this 6311 plus GDP overestimate the charges, while lower set gives the reliable charges of the molecule. Then electronic parameters of this molecule also computed by using the same level of the theory, and these are the that is a picture of the lowest unoccupied molecular orbital, and this is the picture of the highest occupied molecular orbital, and this is the energy, and from this energy we calculate the energy gap. That energy gap is the 3.7 electron volt, and from this energy gap we also calculate the electron, that is potential value, ionization potential value, that is the 5.4 electron volt, while the electron affinity value is the 1.7 electron volt. Therefore, from this energy gap, it is observed that title molecule has the lower energy gap. Therefore, this molecule is soft molecule, so that is more polarizable and has the higher chemical reactivity with the lower kinetic stability. We also computed the various thermodynamic properties of the molecule, like the total thermal energy, total molar capacity, total entropy, and 0-point vibrational energy, as well as rotational constant, by using the B3LIP level with the 6311 plus GDP basis set. And these thermodynamic parameters are quite useful for assess the various thermodynamic stability of the molecule, and therefore these properties also computed by using the DFT. Then molecular electrostatic potential surface analysis. This MEP analysis illustrates the charge distribution of the molecule, that is three-dimensionally. This charge distribution within the molecule that can be gives the study of interaction between the molecule. The different values of the electrostatic potential is represented by the distinct color in the MEP surface. The red color represents the negative electrostatic potential, that is the region of highest electron density, and therefore that is prone to the electrophilic attack. While the blue color in the MEP surface represents the positive electrostatic potential, therefore that is the region of lowest electron density, and that is responsible for the nucleophilic activity of the molecule. While the yellow color in the MEP surface indicates the slight electron rich region, while the green color that is represents the zero potential. Therefore, from this color gradients, we can say that red color having the more electron density, then the orange, then yellow, and then green color, and blue color having the lowest electron density. This is the MEP surface computed from the DFT. That in this molecule, it is observed that the yellow color is spread over the benzodiazepine ring, while the green color, blue color is spread over the 4-fluorophenyl ring. Therefore, this ring is susceptible for the electrophilic attack, while this ring is susceptible for the nucleophilic attack. We also computed the UV spectrum computationally, and that UV spectrum is compared with our experimental UV. This UV spectrum computationally is computed in the gas phase as well as the demeso phase. This is the theoretical UV spectrum that is computed by the DFT level, and that gives the lambda max value at the 367 nanometer, while in the DMSO, the computed value gives the lambda max value as the 375.6 nanometer, while the computed value in the DMSO solvent gives the lambda max value at 362 nanometer. Therefore, it is observed that the computed value in DMSO as well as experimental value are well matches with one another. The vibrational analysis of the synthesized molecule. We take the FTIR spectrum of the title compound that is recorded in the solid phase, while the theoretically vibrational spectra is computed in gas phase at the B3 leaf level with the 6311 plus GDP level. The total atoms present in this molecule is 41. Therefore, there is the total fundamental modes of vibration is equal to, that is 170 according to the formula, that is 3n minus 6. And this is the experimental FTIR value, FTIR spectrum, and this is the computed FTIR spectrum. And we carry out the that is a comparison or between the selected experimental and theoretical vibrational assignments, and it is observed that this experimental peak at the 3337, that is due to the presence of NA stretching frequency, is well matches with the computed spectrum that is at the 3312 centimeter inverse. Also, the aromatic stretching CS stretching frequency experimentally appears at the 2920 centimeter, while the computationally it is observed at the 2902 centimeter inverse. Also, when you look the carbon double bond nitrogen stretching frequency, then in the experimental IR that peak arise at the 1680 centimeter, while in the computed value that is observed at the 1614 centimeter value. Therefore, from all this investigation, it clearly shows that all the experimental frequency is well matches with the computed frequencies. Conclusion: the protocol of the synthesis of the compound reported here is the efficient and afford the product with the desirable yields. Also, the workup of the isolation of the product is easier. Also, there is the no need of column purification, column chromatography purification of the synthesized compound. All the spectra of the compound is ideally matches with the structure of the synthesized compound. Geometry optimization by the DFT clearly shows that this molecule having the non-planar geometry with the C1 point group symmetry. The Mulliken atomic charges investigation shows that the charges are structurally matches at the 631G basis set, while the at the higher basis set, that is 6311 plus GDP, these charges are overestimated. The MEP analysis map indicates the negative electrostatic potential is spread over the electronegative atoms, while the positive electrostatic potential is found around the hydrogens. And when we compute the results of the UV and visible and IR spectra by the B3 leaf method with the 631 plus GDP basis set, shows the good agreement with the experimental values. Therefore, these results clarify that DFT-based computations provide the firm explanation for the reactivity of the title compound. These are some references that is used for this work.
I'm thankful, first of all, to the organizer to provide me this platform to present my work. I'm directly coming to the issue by what. Laser printing is a must for us. It will be to high quality, economical printing and the durability. So it is must-use application for us. But it comes with a problem also, because worldwide around 500 million used toner cartridges ended up in the landfill site around the world. It not only comes with plastic and metal pollution, but it also comes with a very toxic leather toner powder waste, which can migrate from this site through the air. And it's very toxic in nature, and who has categorized this toner waste powder as a probable carcinogen. The used toner cartridge contain 8% of initial toner content as a waste. Whenever we use a laser printer for printing application, it always generates a little amount of residual toner or waste toner, which actually accumulated in that particular compartment in that cartridge itself. So after we exhaust the print cartridge, we discard the cartridge, which also goes with that cartridge. It is contain 8% of total weight. But now initially big market player, HP and Canon, they are trying to utilize the recycle these things, but they are able to utilize 20 to 30% of this toner cartridge for the toner waste powder for the preparation of new cartridges. So still 70 to 80% are going into the landfills. And in fact, globally 6,000 tons of waste toner powder are dumped into the landfill site annually, which is a very problematic one. It's because it's not a carcinogenic nature, but also it can migrate through air because it's small tiny particle. It can float in the air. It can fly. So first, if you want to use this toner laser printing for longer run, we need to find out a solution of it. So first we see what are the components, but what is the composition of the waste toner. It contains mostly 50 to 50% acrylic styrene copolymer, along with 30 to 35 to 40% iron component, along with some other minor components, some polymers, some silica compounds, some dyes, all these things. This acrylic styrene copolymer is very highly stable, both mechanically and chemically, and which actually hinders its recycling. Options are very less because unless until you destroy this structure, polymer, you cannot use it. So we try to use it find a way in our own way. First, we have done a thermogravimetric analysis of the waste toner. And initially, we observed that initially after 2% loss due to moisture, there is a huge loss of 52% material during at 300 to 500 degrees centigrade, which is mainly due to decomposition of the styrene acrylate copolymer. Then it's very drastically slow down the decomposition, and finally it sees weight loss with 36% remaining, which is due to presence of iron component. The loss 300 to 500 degrees centigrade, the weight loss, this slow weight loss is basically due to whatever carbon material remaining is generated during the decomposition of that polymeric network, which is going to the further decomposition for that. As we need a magnetic carbon for the preparation of this material, we collected the material around 600 degrees centigrade. And how we did this thing? We initially took this waste toner powder, then we done a vacuum calcination using tubular furnace, followed by ball milling and mechanical shaving. This is the program, temperature program in vacuum mode we use. And finally, we collect, after sieving, magnetic carbon material below 106 micron. Then we study what happens during this calcination process. When we study the FTIR, this is the ATR FTIR because it is not mixing with the KBR. So it is going ATR FTIR mode. You can easily see that after calcination, this is WTC 600 is after calcination, and WTC RT is the before native material without any treatment. You can see that there are a lot of hydroxyl groups are generated because nitrogen NH2 group is not supposed to generate it in this according to the composition. It is mostly hydroxyl group, and also there are CC bond, CH bond is going breakup here, and nothing is here. So we further confirm this fact by XPS, X-ray photoelectron spectroscopy. You can see that this is the before treatment, this is the after treatment. You can see that a lot of COH group generated plus oxygenate functionality is generated. Also O1 spectra also indicated the same. It is not here, it's very minor here is generated substantially here. But there is no change in the iron component, it is similar almost. Carbonization starts with breaking of different weak bonds and and undergo several kinds of decomposition, rearrangement, elimination, oxidation. These are actually all are radical initiated. These are actually responsible for generation of this hydroxyl group on the surface. And when we did the power XRD, we found that it's identical signal, XRD signal, which is then we studied the ICRTMD database and we found that this signals is basically due to a cubic FeCO4. It is signals of cubic FeCO4. As iron component is not supposed to go any changes during this process, it's 7. It is as expected, it's same. You can change the surface nature of the particle. You can see that this is a polymeric coated material, is showing that polymeric nature. But when you go to the subjected to calcination, it is shrink in size and also spherical in nature due to decomposition of the polymeric material. And this is the TEM. When you study the TEM, initially for this without treatment one, native one, it is not showing very pictures and coming very easily. But here it's very well revealed in case of calcinated one. It's quite expected because this styrene acrylic polymer is very tough in structure, so it's unable to. It's not going. Not that it's not going. They're not allowing the ray to go inside to study properly. So it is quite expected. So also in the ACED pattern of the TEM, you can see that polycrystalline nature of due to this FeCO4 is very easily visible here, very characteristically visible. But here it is signals are weak. It's not very as good as like this. But it's similar, but it's not coming as good as like here. Then we have studied VSM study. This is the variable sample magnetometer study, and to study their magnetic property. You can see that before calcination native one, this is the magnetic property is -40 to +40, but after calcination, its magnetic property increased more than twofold, which is quite expected because breaking down or burning of the polymeric component increase the FeCO4 concentration, and also so does the magnetic property. And also, there's an interesting fact that if you keep the temperature at 600 centigrade and you change the heating duration to see whether it's changing magnetic property or not, it is showing that it's not. If you change the temperature 2 hours to 6 hours calcination, by maintaining the same temperature, there is no change in magnetic property. Finally, we have coated the material initially on the leather surface. Initially, we have done a base coat with a medium strength U binder along with magnetic pigment, IPA, and polydimethyl siloxane and some animal oil. And then we have done plating operation with this instrument to make a base coat, make the surface ready. And then we have done a 10 coat spray by mixing our magnetic pigment, magnetic carbon pigment with PU binder, hard PU binder, casein binder, acrylic resin, and polydimethyl siloxane. And we have done 10 times spray coating on the leather. And by this process, we transfer 2.61 milligram per square inch magnetic pigment per square inch of the leather surface. And finally, we have done lacquer coat and leather ironing to setting the surface. And this is the magnetic property of the leather. This is the magnetic property of the coated leather. When we use native material without calcination, it is little less, but as expected. But after when I use the calcinated one, is showing very high magnetic property. You can see in this video, you can realize that this is the native one without calcinated. This is the calcinated one. You can see it here. So when you bring magnet close to the surface, it is close to the material. It is doing very strong magnetic property even in native material. But this fellow is very magnetic, highly magnetic. It is jumping onto the magnet. It is very highly magnetic in nature. It is black, but it can be made colorful, color leather also, but by changing composition, by overcoating in other color, some crackle finish, different finish can be done. So color can also be changed, not only the black material. And finally, we have tested the coating performance of the leather. We have done roughness, flexing resistance, and abrasion resistance in dry and wet condition. And in case of this is basically a performance of the composition, coating composition, that is formulation. So it is showing that in case of dry roughness, all the materials are very, very excellent. But in case of wet, it's not as part of the dry, but it is still also comparable to the marketed product. And finally, we have done the surface hydrophilicity, hydrophilic property by contact angle measurements. It is showing for without calcinated one, we use without calcinated layer toner, it's been 81.3, and with after calcination it's been 80.2. It is very near to the ideality. It's neither hydrophilic, not super hydrophobic, but it is okay, and it is compared to other commercial products. And what are the use? It can be used for magnetic mobile cover preparation. It can be used for leather apparel, particularly to covering up the zip of the jacket. If you don't want to show the zip, you can use that magnetic things. And you can use a less magnetic button, because most of the things you have to use a magnetic button in leather products. It can be that metal use you can reduce by it, and it can be used as the EMI shielding material, but needs some modification. Still, you have to work on it. We are working on it. It can be used in interior designing. And finally, I like to thank my team member, Mr. Nayan Sarkar, Mr. Subit Mondol, and Dr. Murli Satish for their cooperation and help to carry out this investigation. And I would like to thank my HOD and my director for their encouragement and support. And thank you all for your presence hearing. I would like to thank everybody present here for their presence hearing, and I would like to wish everybody a very happy new year. Thank you very much. If you have any question, I would like to answer.
Okay, thank you.